Ready? Okay, hi, it's Tracy again. This is part 3 of the lab, and we're gonna deal with this really cool thing called the bridge rectifier, right? So earlier we saw that with previous cases, when we didn't have the capacitor, or even when we had the capacitor, that the wave that we got was a sawtooth wave. But when we're trying to replicate a DC, trying to replicate a DC current, we want it to be straight and horizontal. So now we can look at bridge rectifiers, which is essentially like 4 diodes and oriented in a specific orientation. That is really cool because it compensates based on the phase of the current. But we're gonna investigate different results using different capacitors. In the first case, we'll be dealing with a 0.1 microfarad capacitor. Using LT-Spice, we see that basically we have, if we try to trace the direction of current, we have an AC sine current, right, flowing through there. When it's in positive phase, it'll go through here and deposits in the capacitor and the resistor, which as shown in a previous part 2, I've already described the effect of that. What's so cool about this bridge rectifier is when it is in the positive phase, the only direction that flows through is here, diode 2 from the positive side, and it returns through diode 3 on the negative side. So when it's the positive phase, it goes through diode 2, and when the AC current switches to the negative phase, instead it goes through diode 3. So this allows the wave to keep going despite changes in phase of the AC current. So you won't see that stop and then the arc that we saw in the last part. So we tried this for different capacitors. So the idea is, as you increase the capacitance, it's gonna store the charge more in the capacitor, which allows better compensation into the resistor, right? So with a 0.1 microfarad capacitor, we still see the really strong sawtooth wave. Here, the blue line is for input, which is like the voltage, and then the green line is for the output, which is the the potential difference across the resistor. So when it's at a 0.1 microfarad, you can still see that sawtooth wave. But as you increase to 1 microfarad, you see it's barely visible, and at 100 microfarad, it's essentially invisible, and it's very straight. And from afar, this just looks like a DC current. And so we actually tried to run this on our breadboard. The ballast we used for resistance was actually 9.808 kilo ohms. Actual capacitance, when we had the 0.1 microfarad capacitor, we measured it to 0.10821 microfarads. 1 microfarad results in a 0.98399 microfarad, and the 100 microfarad capacitor we used was actually 91.644 microfarads. This is actually really close, so I don't think it will pose an issue. And